Hello everyone. In this particular small lecture, we will be discussing about hash function. Hash function is a mathematical formulation that converts any numerical input, and that input could be of any size, and that would produce always an output which is of fixed length. And the output that you generally get is called as the message digest or called a hash value. So a hash function, what it does, it maps the keys to a small integers, which is called as buckets. So what is meant by all of this is it's like mapping key to its value, a key value pair that is being created over here. And that mapping is termed as hashing algorithm. So a key could be considered in a data structure kind of thing is that let's suppose that you are maintaining a record of all the students. I'm maintaining a record of all the students in this class. So I would have a roll number, I would have name, what is the grade and other things. So roll number, then name, maybe the address, which is not relevant, but still grade, which is what you have got the grade and other things. So if you see that name could be same, address could be also same, grade could be same as well. The only identifier that can distinguish between different people over here is roll number, and that is termed as the key, which is this is an identifier which we would be taking to map the input using this particular key. And assume there are n records, you can apply insertion algorithm, you can apply deletion algorithm, you can search another thing. So let's suppose if you are maintaining a data structure of all the values that you are getting, and this structure contains 5, 7, 8, 9. So one way is that you can arrange them in an array, and then what you can do is that if a particular entry is there, you can mark this as 1. If that entry is not there, you will mark this as 0. So let's suppose this is 0, 1, 2, 3, 4, 5, and so on. Let's suppose 6, 7, 8, 9. So 6, 7, 8, 9. So 5 is there, so you will have 1. 0 is not there, so all of these entries would be 0. 7 is there, so you will mark this. 8 is there, 9 is there, and then is stored. So this is one way of having a record to check basically if that record is present in the system or not. But what if the data contains a very big, which is 9173? So in that case, you have to produce a very big array where you would have to store, and there would be so many empty list. So that is the reason we do not want to store this in an array and just it's not memory, I would say, efficient. We want more of a memory efficient algorithm. How do we achieve it? Using hash tables or hash table. Hash table is just a table which contains n input in an m buckets, and I will try to explain it to you. But one use case that you can see in this hash is whenever you are storing your password and other thing, this message gets transmitted to a hash algorithm that produces a hash value. That the beauty of a hash value is that input can be of any size. The output would be always of a fixed length. It is deterministic, that the same input always gives the same output. So if you are passing 1, 2, 3, 4, it would be producing the same hash value which is of that fixed length. It is irreversible, so you cannot pass the output back as an in the system to produce the input back again. So it is irreversible. Then another important property is that output changes dramatically with a small change in the input. So if you are passing 1, 2, 3, 4, and if you make it as 1, 2, 3, 5, you will see the hash output is completely different. And the last but not the important benefit of using hash function is it is fast with low computational overhead. It is computationally very fast, and most of the researchers do use hash algorithm in computing this hash value. So examples of some of the hash function, as I said, is it is a mapping of a key with respect to a a bucket that you are storing, and this bucket could be arranged in the form of a table. So let's suppose you have a key K, and you have bucket or a table which you are maintaining from 0 to m minus 1, where m could be of any value which isn't closer to 2. Let's suppose if I apply k mod m. So let's suppose h of k, if you remember what is modulus operation, that would give you the remainder value. Let's suppose if I want to pass 512, 512 modulus m, and let's suppose if I am storing this value to mod m, which is 10. So in this case, it would be 9. So 512 mod 10 would be storing the value at index location 2. If another key comes in, another value comes in, then we would be storing it. Let's suppose if it is 514, we would be storing it at index location 4, and so on. So we would be maintaining this, and this is one of a very like it's a hashing by division. You are dividing each of these numbers in order to store a particular value. But now let us suppose if you are if you get the same value, like 512 modulus 10 is 2, but let's suppose if I get another value which is 312. 312 modulus 10 would always land up in that same slot 512. So what people have done is that either they maintain a linked list kind of thing. So what they do is that they append another data structure after that. So 312 would be stored at the next location. And if 412 comes in, then it will store, if it's already there, like a an item is already there, it is also termed as collision. Collision is happening, then it will look at the next value, which is 312. 312 is also that slot is already occupied. Collision, again, collision happens, then it will store the value to the next next linked list value, and so on. So this is one way of achieving like more entries could be stored, because you cannot store so many values in a hash table which just contains 10 elements. You are just storing 10 elements. So you need a better data structure. Either you apply a kind of linked list. But the problem with the linked list is, let's suppose all of the values that you land up is in this particular linked list only. So what about all these slots? That gets wasted again. So what is a better approach? Another better approach is using open addressing, that I will also discuss. But open addressing is, rather than storing it in a linked list, you store it in this original data structure only. You pass on to the next value, and so on. So this is one way, as I said. Example of a hash function is hashing by division, that you apply a modulus operation and find the remainder value and put that value over there. Another one is, but here in this case, if you choose a prime number that isn't close to power of 2, then this kind of hash function is a better approach. But if you will use a hash function which is closer to 2 raised to the power of 3, you should apply hashing by multiplication. And this hashing by multiplication is one algorithm that is another kind of algorithm that people do use, where what we do is that first we take a key k which is of w bits. So let's suppose that you choose that I want to use a key which is let's suppose 107. Let's suppose first we check, first we see that w bits that I want to apply an encryption, or apply, sorry, not encryption, hash function on all the key values that I'm getting should be of 7 bits. So w is 7 bits. So let's suppose if I take key as 107, I will convert this into its binary equivalent, which is 1 1 0 1 0 1 1. Okay, that's its binary equivalent of key k, which is 107. Then I will also choose a random value of a. So let's suppose I choose a random value of a, which is 185. So 185 hash value is 1 011 001. Okay, then I apply a multiplication operation. So over here I am multiplying a with k. So this a and k would be multiplied. 107 times 185 would give you the value 19795. The output would be of w bits, 7 bits times 7 bits. So the output that I get is 10011010101 uh, this is 100110101, then 01, and this is 1 2 times 3 times, sorry, 1 times 2 times 3 times 4 times, and then 0011. Okay, then what you do is you just take 2 raised to the power of w bits, which is 2 raised to the power of w bits was 7. And here what I am doing is I'll be just taking 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit. I will be excluding all of this, but I will be taking just interested in this. Then I will apply a right shift operation on W minus R bits. So W minus R bit, here I am applying the message is 8. Like I choose a value which is 8, which is 2 raised to the power of 3. So which is in the form of 2 raised to the power of r is 3. So w minus r bit, which is w was 7, minus r, which is 3, which is equals to 4. So what I'll do is I'll exclude these last 4 bits, and whatever is the resultant, that would be the hash output. So hash of 107 would be 101, which is not 101, that is the binary value. So 2 raised to the power of 0, 2 raised to the power of 1, which is 4 plus 1, which is equals to 5. So the hash value for inserting this key, which is 107, would be 5. So you are storing this value in the bucket number 5. So you can achieve this hash function either using division operation. Division operation is utilized if you choose a value or choose a prime number that isn't close to the power of 2. But if you choose that, then it is better to utilize this kind of algorithm. The other thing is the load factor, which is used to determine how well the elements in the hash table are distributed. So this load factor is generally the number of stored elements in the table divided by the total capacity of the table. So n over n. So let's suppose if you have m slots, which means that you are doing 0, 1, 2, 3, 4, 5. So this is 0, 1, 2, 3, 4. I'm using a mod of m, which is mod of 5 in this case. So 0, 1, 2, 3, 4, 5 elements. And let's suppose that all the elements are stored, which means that first value was stored, the second value was stored, the third, fourth, if you are applying these 5 keys. In that case, the number of elements are already stored, so it would be 5 elements over 5, so the load factor would be 1, which means that it is completely filled. Versus if the elements are 3 elements are stored in 5, so the load factor would be 3 over 5, which is 0.6, which means 60% of the hash table is filled. So you can check how exactly your table is presently in terms of the number of elements which are stored. So I had discussed about open addressing. Open addressing happens when the collision is happening and when you are storing the elements in a linked list. You are storing all the values in a single linked list which is stored. The complexity is very huge in this case because the worst case complexity is very huge, because then all the elements get stored in a single linked list which is at a particular value. So one way to achieve this collision is that instead of storing it in the same linked list, what you can do is you can store it in the same hash table. And for that, you apply different kind of technique, which is one is called as linear probing, or another one is quadratic or double probing. So in a linear probing kind of thing, let's suppose that here you apply the hash function hk plus I, which is the index modulus m. What exactly happens over here is, let's suppose that you have a hash table and you are storing all these values, which is 12, 13, 24, 35, 88. This is once again on mod of 10. That's why 9 buckets are stored over here, 0 to m minus 1, which is 0 to 10 minus 1, which is 9. So you have stored all these values. So h of k, which means hash of 12 would give you 2, hash of 13 would give you 3. Here you are applying hashing by division algorithm. So now let's just suppose that you are passing the value 82. So hash of 82, which is 82 modulus 10, in this case would give you 2, but there is already value over here. So there is collision number 1 that has happened. So what you can do is, you can change this value to plus of 1. So you started with 0, then you will check with plus of 1. So this will give you 3 mod 10, which would go to this value, which is third index. Value is already present. So once again, collision happens. Then apply 2, then apply 3, then apply 4. So you will see that all of these gets, there is no place over here. The next available slot which is available is at index location 6. So 82 would be stored over here. So that is linear probing, storing the elements. Whenever you find a open slot, store that element over there. But the problem with this open addressing is that for lookup operation, if we get an empty slot, means the element is not present. What does that even mean? So let's suppose if you have all the values which is stored 12, 13, 24, 35, 82, 34 and 88, and then you will, let's suppose the first one is that you are inserting 34 elements. So 12 is not, it's already filled. 34 has to be inserted. So you will check for fourth index. 24 is present. So you will go to the next. You will go to the next, and then you will store the value. Next, you have to delete 35. So you will go to the index location 5, and 35 is present, and you will delete that particular slot. Then you have to search an element. So in that case, when you have to search, you will go to that index, which is at fourth location, and 24 was there, so it will go to the next, but next is empty. So in that case, it will never go to the next, and the output element would not be processed, and it would say that that element is not present. So for a lookup operation, if we get an empty slot, means that element is not present in the table. So that is one of the issue. The another issue with that is primary clustering. Linear probing, this particular algorithm does probing on each slot one by one in a circular fashion. So one by one elements are inserted. In the above elements, let's suppose in this case, all the slots are filled except slot number 9. Let's suppose all these elements are stored. So now let's suppose element 100 is required to store. Probing would still be done from 0 to 9. And that's the size of the table. That's the entire table. The time complexity is no longer constant, even for lookup operation, and that is called as primary clustering. You cluster all the elements. So in order to get rid of both of these problems, there is another way that you can achieve. One is quadratic probing, and the other one is double probing. So double probing is that first you apply a hash function, then once you are passing that index, you apply another hash function and then do a modulus operation. So you are achieving another you are achieving a much better way of storing these elements, and this is much better in comparison to the previous algorithm, which was just linear probing. Most of the organizations do use this double probing, and the sequence becomes more random and in that case, you can achieve better results. There are some popular hash functions which are available in like mostly people have used. You might have also heard SHA algorithm, which is secure hash standard. It is SHA-1, SHA-256, SHA-512. There is also MD5 algorithm. In this case, I'll be just in this class, I'll be just covering SHA-1. So in the SHA algorithm, what happens is that SHA-1 algorithm, the input is of any arbitrary length, but the output that we get is of 160 bit. That's what SHA-1 says. If it is SHA-256, the output is 256 bits. If it is SHA-512, the output is 512 bits. So here what happens in SHA-1, as I said, the output is of 160-bit value that we are getting. The input that is generally inserted in this algorithm is 512 bits. So how do I make it as 512 bits? So let's suppose if you are passing just 2 bits as an input, you will add an extra 510 bits in order to make it as 512 bits. So you add some padding in order to get this as an input to this algorithm to produce an output which is 160 bits. So always the input is of 512. What if it is greater than 512? So let's suppose 514. Then in that case, it will be passed as two different inputs. So it would be 512 would be passed as the first input. The leftover 2 bits, which would be appended with next padding, which is 510 bits of padding, and it would be fed as an input for the second round. Not the second round, but the second time this overall algorithm would be done. I'll try to explain this once again and then I'll cover. But now let us presently suppose that the input that you have is of 512 bits or less than that. So if it is less than that, you add a padding. If it is if it is 512 bits, you will just pass this in and the input to this function. So here this overall algorithm comprises of a compression function, where compression function takes an input as a 512 bits and converts it into the output, which is 160 bits. How do I convert it? It is based on this 512 bits are first converted into words. So if you recall, when I was covering AES algorithm, you were dividing 500, the word is of 32 bits. In an AES algorithm, we covered that a word is of 32 bits. So if I want to convert this 512 bits to a word, I will divide it to by 32. So I will get 16 words in total. These 16 words would be passed as an input to this compression function. This compression function in all contains 80 rounds. Okay, so word 0 will be passed over here, word 1, word 2, word 3, word 4, word 5, and so on. So here in this case, the numbering is incorrect. This is 1, 2, 3. I excluded 1. So here in this case, 16 words are being calculated. So after word 15, when we will receive for word 15, all the inputs are done. In that particular case, what we will do is we will be passing then again word 0, word 1, word 2, word 3. So total, once again, all these words would be sent until and unless we receive, we get into round number 80 in this particular case. So what happens in each of the round? That's the another thing that we have to cover. So in each of the round, we will have an input as word 0, and we would also have another input which is 160 bit, which is called as initialization vector. When I was initially talking about cryptographic algorithm, I had discussed about different kinds of technique. In that, I had covered initialization vector. That initialization vector is a vector which is passed as an input. If you do not recall, let me just open that quickly. 1 second. think I had discussed it. 1 second. Give me 1 second. Just um. Yeah, here. So if you see, initialization vector was among these modes of operation that I was covering. And here was the initialization vector, which was taking in as an input and it was producing the output. But anyways, so here initialization vector is of 160 bits, which is given, and that is passed to round 0 with an input which is word 0. So this initialization vector is of 160 bits, which in turn is divided into 32 bits. So which means that we can produce nearly 5 blocks. So each of the block is of 32 bits. So this is 32, this is 32, 32, 32, 32, 32 times 5 is 160. So total of 160 bit uh, initialization vector is created. So the first 32 bits, we will take the first 32 bits and we will shift, 5 bits are shifted left. 5 of the bits are shifted left in left direction. Then what happens is that the next 32, 32, 32 bits are passed into process P that will produce an output that would be added with this the first operation that you have done, which is shifting operation, that would be added, and the last 32 bits are added together. That will be added, all of them would be added, and the output would be passed as an the word 0. If you recall, this was word 0 which we were taking. So word 0 would now be taken into consideration to process. So here in this case, word 0 is taken, and then this is passed to this addition operation. This addition is not just adding, it is add modulus m, where m is once again changed over here. That output, like add mod m, add modulus m, we would get an output. Here in this case, we will be passing through a constant key, which is k, some kind of constant. That constant is basically round, dependent on the round, that k constant would be chosen. Then the output of this would be considered, would be passed as the first 32 bits. The next 32 bits would be the previous a bits. The next 32 bits would be the b bits. The next 32 bits would be the c bits, and next 32 bits would be e. So you are shifting. B becomes a, c becomes b, d becomes c, e becomes d. And the first input that you are getting is the output. Remember, in LFSR also we were passing in the fiscal structure also, we were doing some kind of processing like that. So we shift each one of them, and the first one is the process, which we have just covered over here. So what happens in process P? That's the first question. And the other question is, what is this key key constant which is we are taking, and why it is dependent on T of I? So as I said, in total, in Asha algorithm, the total of rounds that are done is 80 rounds, which in this case is that every time word 0 would be taken and some constant k would be taken every time in each of these rounds. So if it is first four, it is divided into 4 stages. So when, if it is between 0 to 19, 0 to 19 round, then one single key would be used. When it is round, when it is stage 2, which is from 20 to 39, then key k would be changed. Then if it is 40 to 59, another key would be used. For 60 to 79, there would be another key which would be used. So in all, 4 keys would be created, and depending upon which round it is, it would be passed as an input. So if it is T of I, T of 1, T of 2, T of 3 to T of 19, then a single key, same key would be used. For another round, which is round number 20, in that case, key K2 would be used, which would be another key. And generally, this is the key structure over here for round stage one, this is the key for the next one, this is the key for next stage, and this is for the next stage, depending upon on which round it is. The fiscal process, which is over here, is also varied depending upon which particular round you are at. So this particular process P is generally, if it is stage 1, which is 0 to 19, then you take the B bit, you take the C bit, B and C, or you will take not of B and D. You will be taking these input, this. So if you see this B, C, D, these are the input, right? B, C, and D. This would be passed over here, where you would be depending upon on which round you are. So let's suppose if it is between 0 to 19, then B and C would be AND, then the output would be OR with not of B and D. If it is round number 20 to 39, in that case, this process would be used as a process operation, and so on. So you can understand the complexity of the overall algorithm. In all, we are getting the final, 80 rounds, and each of them, this process is happening, and every time different kind of, depending upon which stage you are at, you are getting a different key, you are getting an output, where you are performing the process operation, which is different. In the end, we will get an output which is 160 bit, which would be the hash output. So you can understand SHA-1 is so complex. But as I said, what happens when if it is more than 512 bits? Then in that case, what happens is that, let's suppose if you had an input which is more than 512 bits. So let's suppose if it is 514. So 512 would be passed as the first round. The leftover 2 would be added, would be adding padding. So it becomes 512 bits. So here the output would produce you, you will take an initialization vector, you will take key, you will perform some operations. So there is an initialization vector which is passed in order to get an output as 160 bit. Here in this case also, you will do the similar kind of processing of all these rounds, but the initialization vector would be of the output that you are getting from the previous round. So initialization vector, which is of those 160 bits, where you were dividing 32, 32, 32. The first initialization vector would be the output of the previous one. And that's what we had covered when we were covering the mods of operation, where how does the value changes in general. So here is it, right? Let me open it once again, sorry. Here, see, this was the one that we were doing. We were here initialization vector was taken, then we were performing some kind of encryption, and the output of this would be fed as the next input over here. Here also we were shifting, and then once again all of this operation was done, which is an example of cipher feedback algorithm. Or you can use it as a cipher blocking technique, where the plain text, the initialization vector was taken, the output of this cipher text was taken as an input to the next round. That's what is done over here. So it is a typical example of this algorithm that we just discussed. The initialization vector becomes the output of the previous block. So what are the applications? One of the applications that I discussed was when you are storing the username and password. You can pass this password, which is very uniquely identified to a particular person. They pass it to a hash algorithm that would be stored. So the table that would we would contain would be the username and the password. So if a attacker even gets a hold of this username and password repository, would not be able to identify, because it is the hash output. And as I said, hash is irreversible. You cannot pass the output as an input back again to get the input. So even if the attacker gets hold of this, would not be of no use until and unless he knows what is the SHA algorithm. But even though if he knows, he doesn't would know what is the input which is given. So it is irreversible. So password storage is one of the example. The other one is the data integrity check, which is what information that you are passing, the hash value would be exactly same if it is received at the receiving side. If it is modified, the hash output would be different. So that's what we had discussed in distributed ledger technique in Tangle CV when the original data was sent, and if you pass that ledger, you take some nonce value and you pass this into a hash value that is passed to another block, um, and you were maintaining all of this. So even if somebody tries to modify some data in this ledger, the hash output would be different. So you will be able to identify that there was a discrepancy between the two documents which was shared. So that's all I wanted to cover in this class. We will meet next week and discuss about the projects. I'm very much excited on how you have created your projects, and we'll discuss about that. Okay. Till this, everything would be covered in your final exam. Take care, everyone.